Hey everyone, and welcome to another week of PChem recitation prep. So in this video, what we're going to be talking about is going over some basics of double integrals, the ideal gas laws, and the kind of four laws of Thermo. We'll explain that in just a second, but wait for that till we get there. So, for basics of double integrals, I realize a lot of you guys are pretty apprehensive about what to do with double integrals, maybe because you've never taken a class on it or something like that. But let's step through a couple things that you need to know for double integrals. So first off, when you take a double or more integral, you work your way from the outside in. So this applies if you're taking with respect to the same variable or if you're taking with respect to different variables. So with the below equation, we have the double integral of 5x squared plus xy plus 10y to the third dx dy. So with this one, what we're going to be doing is taking the integral with respect to y first, and then we'll take the integral with respect to x. If we had something where it said dx, then you would just take it twice, but you would need to make sure that you take it with respect to itself each time that you go through the step. That's very important. So for this first one, we're going to take the integral with respect to y. So since we have y as the outmost variable, we're going to apply it to all of the things within there, and then we're not going to forget our plus c term because this is an indefinite integral, and we're going to be using that when we actually take this next integral. So now we're going to take the integral with respect to x, and then we get our final equation of f of xy. So for this, we're going to get 5/3 x to the third y plus 1/4 x squared y squared plus 5/2 x y to the fourth plus c times x plus d. So this c variable we don't know because that came from the y equation, and it will be involved in the integral for x, which was very important. And then we have an additional unknown variable d, which came from the integral of x. So in order to solve these, you would have to be given some parameters, and you would be able to back calculate from that point. Okay, so now let's go on to the ideal gas laws. So this first one that we have is Boyle's law. So what Boyle's law tells us is that the pressure is inversely proportional to volume. So this is where we actually get that P1V1 equals P2V2 equation, which will apply later on. And then for Charles' law, we get that volume is proportional to temperature, and that pressure is proportional to temperature. So for this, we get two different equations. We get P1 over T1 equals P2 over V2, or T2, and we get the same thing for volume. And then for Avogadro's law, this tells us that the volume is proportional to the number of molecules that you have in a system. So remember that this is number of molecules, not moles, so that capital N gives you number of molecules. We use the smaller lowercase n for moles. So again, you all should know this, but you just divide by Avogadro's number, and you'll be able to get to moles in that case. So when we combine all of them together, this is actually where the ideal gas law comes from. So we get this pretty big equation at the top that is equal to a constant, and when you rearrange it, you actually get the PV equals nRT equation. Okay, so one thing to note is that R can come in multiple forms depending on whatever units you are using. So some of the big ones that we're going to be using is 8.314 joules per k-mole, 0.0821 liter atmospheres per k-mole, and 8.314 liters times kilopascals per k-mole. So just make sure that you use whatever you have as far as the other units available in your equation and move forward from that. So next, we're going to be going over the laws of thermodynamics, and this is kind of where the fourth one comes into the situation. So the zeroth law is actually a mathematical property, so it's the transitive property. So if we have A is equal to B and B is equal to C, then A is also equal to C, and that applies to thermodynamics as well. So moving on to the first law of thermodynamics, we're going to be talking about energy, and energy cannot be created or destroyed. So it's saying that the total energy is equal to the energy of the systems plus the energy of the surroundings, which is going to be equal to 0. So if we rearrange this equation a little bit, we get the change in energy of the system is equal to the negative change in energy of the surroundings. But how do we go about changing U? So we can use Q and W. So remember that Q is the measure of energy or heat flowing across a boundary, and W only changes when the volume changes. So that's really important to remember. So delta U is equal to Q plus W. And remember that Q is not equal to the change in temperature. Q is equal to the heat capacity times the change in temperature. So if you're at constant volume, you're going to have Q is equal to CV delta T. And if you're at constant pressure, you're going to use Q is equal to CP delta T. Additionally, with the first law, under constant volume, all heat applied to a system will be used to increase the temperature and no work can be done. So since there is no change in volume, our overall work equation is going to go to 0 because work is equal to negative P exterior times change in volume. So that simplifies our energy equation by making it delta U is equal to Q. And then under constant pressure, heat and work can be applied to the system. So our change in energy is going to still be equal to Q plus W, but we can replace W with P external delta V. So we get overall delta U is equal to Q minus P external delta V. And then what we can do is rearrange that a little bit so we get Q is equal to delta U plus P external delta V. And remember that Q is equal to delta H at constant pressure. So we get delta H is equal to delta U plus P external delta V. So bringing this all together and helping you solidify it a little bit in your brain, when you have constant pressure, delta H is equal to delta U plus P delta V. And then at constant volume, delta H is equal to delta U plus V delta P. Okay, moving on to the second law of thermodynamics. This has to do with entropy. So all spontaneous processes go to increased disorder, or the entropy of the universe is always increasing. So we're going to look at this in two different ways. So there's the statistical way to look at it and the thermodynamic way to look at it. So the first one we're going to look at is the statistical definition of entropy, which looks at capital W, which is the number of ways to arrange something. So for this, there's quite a few equations that you can actually generate for this. So we have S is equal to the Boltzmann constant times the natural log of W. This is also equal to S is equal to the number of moles times R times the natural log of W. And remember that in this case, S, or entropy, is equal to joules per Kelvin. The Boltzmann constant has units of joules per Kelvin, and then R, we're going to be using the joules per kmol version of R in this instance. So when we're looking at delta S of a system, you always do S2 minus S1, which is also equal to the Boltzmann constant times the natural log of W2 over W1. Because remember from our log rules that the ln of W2 minus the ln of W1 is the same thing as dividing W2 by W1 within the natural log equation. So again, you can substitute the Boltzmann constant for your number of moles times R. And now we're going to look at the thermodynamic definition of entropy. So for this, we're going to be looking at an isothermal system. So delta S is equal to Q reversible over T. And remember that reversible means that the net delta S of a system and surroundings is going to be equal to 0. So from that, we can show that the delta S that is equal to Q reversible over T, not delta T, just T, is equal to the Boltzmann constant times the natural log of W, which we just got from the statistical definition. So the way that we go about doing this is we define capital W, or the ways that things can be arranged, is equal to the volume raised to the n power. So this is going to be whatever amount of molecules that you have in a system. So we're going to further plug that into our equation and have delta S is equal to the Boltzmann constant times the natural log of Vf raised to the n over Vi raised to the n. And again, that simplifies to the Boltzmann constant times the natural log of Vf over Vi raised to the n. Then what we can do is say that Q is equal to the negative P delta V. And remember again that P is rearranged to equal nRT over V. So we can take the integral of Q with respect to V, and what we get is that Q is equal to nRT times the natural log of Vf minus ln of Vi. And again, that rearranges to nRT times the natural log of Vf over Vi. And we can plug that into our Q reversible from way up above and get that the change in S is equal to nR times the natural log of Vf over Vi. So this brings the two equations together, and really it just is dependent on how you want to go about defining them and what information you're given in your question and how you're going to go about solving for entropy. So looking at the third law, so this states that entropy can be determined absolutely. So there's another way of stating it, that at absolute zero, there is going to be zero disorder, or things will be perfectly crystal. But something to note is that G and H cannot be determined absolutely. That's why we have to define them at STP, or standard temperature and pressure. So remember that at STP, temperature is equal to 298 Kelvin, pressure is equal to 1 bar, and our number of moles is going to default to 1 mole. So using this information will help us to gain insight on the system and how it deviates from standard temperature and pressure. So at constant volume, we have a thing called the Helmholtz free energy, which is denoted as A. So when we do that, we have delta A is equal to Q minus T delta S, or delta U minus T delta S, which we don't really deal a whole lot in constant volume situations in biology and biochemistry. Most of our stuff is done at constant pressure. So we're going to be using Gibbs free energy, which is defined at constant pressure. So for us, we're going to be using delta G is equal to Q minus T delta S, or delta H minus T delta S, which I'm sure you all have seen in some of your earlier classes. Now remember that delta G at equilibrium is equal to 0. Delta G for a spontaneous reaction is negative, and delta G for a non-spontaneous reaction is positive. So that's all I have for this video today. If you guys have any questions, please feel free to email me or post some sort of comment on here. Otherwise, have a great rest of your day.